All right, so in this video, we're going to be looking at properties of functions, and we're going to be using piecewise graphs as our example. Now, for piecewise graphs, if you have the set of equations, they will usually give you the domain of the function in the inequalities that are included in each of the pieces. Now, one thing that you need to consider when you're doing domains, though, is that you should write the domain as a single interval if there are no gaps in it. Most piecewise functions do not have gaps. They will, for instance, if they say this piece applies for x less than 4 and this piece applies for x greater than or equal to 4, do not write one interval for -infinity to 4 union 4 to infinity, because there are no breaks in the graph. Using multiple intervals is only to be done when there are breaks. Most piecewise functions do not actually have gaps in the sections unless the segment itself has a break in it. So that's something that's very important, because even though it is not technically completely wrong to write multiple intervals with unions between them, it is mathematically inelegant, and you will usually get marked wrong for doing that. So when we look at our first graph right here, the thing that we want to notice is that, again, there are no breaks when you look at your x-axis all the way across. There are no jumps. There are no values that are skipped over. So we would say that this domain is -infinity to infinity. It's all real numbers. Now, the other thing to keep in mind here, regardless of the technology you use, if your graph goes all the way to the edge of the graph, whether there's arrows labeling it or not, the graph continues past the edge of the graph. The only time that you should assume that a function stops at the end of the graph if it is labeled with a dot and a closed or open circle. Otherwise, it's just the end of the graph. Assume that the graph keeps going. For the range is important for piecewise functions. The range is very difficult to obtain from the function and not from the graph. So generally speaking, if you want to obtain the range of any function, it's going to be easier from the graph. But particularly for piecewise functions, if you need the range, graph it first. Now, the range, of course, is determined by the y direction. So I recommend starting at the bottom of the graph and going up until you find the first value or you find the first segment. If you immediately find the first segment at the bottom, then it goes all the way down to -infinity. But if there is a minimum to the function, as there is here, then you would go up until you find the first y value. In that case, that's going to be 0, and it is included because this is a closed circle. And then how high does it go? In this case, it goes to infinity. Now, in some of the other graphs, we're going to look at some other kinds of things that can happen with piecewise graphs. But in this particular case, the range is also just one interval. Now, one other kind of thing to keep in mind when we're doing functions of any sort is we may be asked to identify where the function is increasing or decreasing. When a graph is increasing, it is going up and to the right. Increasing is not going up to the left. Increasing is always going, if the y value is increasing as x increases, so as x goes positive to the right in this direction, then is y increasing. And then the interval is reported as an interval in terms of x. So in this particular case, the graph is increasing from 4 to infinity. The endpoints are generally never included in these intervals. Is there any section of the graph that is constant? No, not in this graph. And then decreasing is going to be, in this case, from negative infinity to 4, because that is this section of the graph. Again, as you go positive in x, what is y doing? Y is going down. So that is the decreasing section. Are there any maxima or minima? There is no max. In this case, the minimum is at 0, and specifically at 4, 0. The minimum itself is 0, and you can see that reflected in the range. Now, one of these pieces has only a open circle on it, and it's covered up by the fact that the other piece starts with a closed circle. We cannot tell from this graph because they overlap which piece is open and which piece is closed. Changing them would not change the behavior of the graph at all, and it would not change the value of the minimum in this case. All right, so let's walk through this again, but now also let's look at the next graph. So here's our second graph, and so let's also go through the domain and range, and then any increasing, decreasing, minimum, maximum. Now, in this particular graph, again, we see that the domain is actually all real numbers. This section of the graph goes up to, but not including 1, and then this section starts at exactly 1 and then continues. So there is no breaks in the domain, and so the domain is also all real numbers. So negative infinity to infinity. Now, what about the range? Now, here we do have to write our interval in 2 segments. And the reason for that is because as you go up from the bottom, there is a gap in our graph. There's a break where there's no values going on. So even though the overall thing is like, yeah, this side goes down to negative infinity, this side goes up to plus infinity, negative infinity to infinity suggests that every possible value is possible. And that's not what's going on here. Every possible value is not possible. So what are the possible values? In this segment of the graph, the maximum here is 0. So this section will go from negative infinity to 0, and it's included because 0 is a value on the graph. And then union, and then here's our jump. The next smallest value is 3, and it is also a closed circle, and then up to infinity. Now let's think about our increasing, constant, and decreasing. There's also constant intervals that are none here, so we can just put those to the side. Where is it increasing? So in this case, it's going to be increasing in 2 intervals. So it's coming up from the bottom. This is all increasing again. Remember, as x is positive, what is y doing? This is increasing. As x increases, y is increasing. So, but it only goes up to 0. So negative infinity, comma 0. Again, no endpoints. And then where does it increase again? It increases again when it jumps to the second piece. And so that's going to increase again. Remember, in terms of your x values, it's going to increase here starting at 1 and then going up to infinity. Where is it decreasing? Well, it's going to start at 0, where this graph turns over, and then it's only going to go to 1, because again, that's where it jumps up and then starts increasing again. What about a maximum? There is no maximum. And what about a minimum? There is no minimum because the largest value on this graph, at least not globally, it goes to infinity, and the smallest value on this graph also goes to negative infinity. Now there is a local maximum at the point 0, 0 on the bottom section of the graph, but it is not the global maximum of the graph. Now, the fact that it's local might be important, so it's worth identifying that. And there is another local minimum at 1, 3, because at least on this section of the graph, that's as small as it can go before there's a jump over to the other graph. But these are not global. And if the graph doesn't specify, then they're thinking globally, what is the minimum or the maximum? All right, so let's look at our third graph. Now, let's also go through these same questions. So what is the domain? So again, we start at the left end of the graph. We see graph, 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 graph. There's open circle. It jumps to a closed circle, which means the point is included on at least one section of the graph. That means it's in the interval, so there's no break in the way you write the interval, and then it continues and it continues. And again, the arrow indicates that it reaches the end of the graph, that it continues in this direction. So this will continue to get wider, and so it will eventually go to positive infinity. So negative infinity to infinity. Again, like most piecewise graphs that you will encounter in textbooks, they go on forever off the edge of the graph. Again, you have to look for those open or closed circles at the end to tell you that it's actually stopping. Now, what about the range? Now, the range in this is also going to come, as our previous section, in 2 pieces. But in this one, it's particularly interesting because this section of the graph is a constant. How would we represent a constant in the interval notation? The answer is you don't. You represent it as a set, a single value. And then you union that with the interval that applies to the rest of the values, which in this case would start with and include -2, and then it goes up continuously to infinity with no additional breaks. There's no additional gaps in the graph. So points are represented inside curly brackets. They're not really written as intervals because it's a single value. What about increasing? Increasing, again, in the x direction is what you want to keep in mind. This is going to start at x equals -2, again, here. And then it's going to increase, and then even though the section changes, it continues to increase. Decreasing, no intervals for where it decreases. Where is it constant? In this case, it's going to be constant from negative infinity to -2. There is a minimum at y equals -4. Something to keep in mind here is that this minimum is actually occurring on that entire constant interval. So you can't really write a point. It's not a single value, but that is the minimum value of the function everywhere. There is a local minimum at the point -2, -2. It is not the global minimum, but it is a local minimum in that every value around it that is connected to it is the smallest possible value. So you could specify that. But again, if it's not labeled as local or global, they mean global. And so that minimum is at -4. Is there a maximum? There is no maximum because the y values go up to infinity.